Look up at the sky. 93 million miles away, our sun burns with unimaginable power. For billions of years it has driven life and weather on Earth, powered by nuclear fusion, the process that forges elements in stars. Humanity has long dreamed of capturing this stellar fire, building a small sun on Earth. Fusion promises clean, safe, and virtually limitless energy, no carbon emissions, no long-lived nuclear waste. Unlike fission, fusion combines light elements like hydrogen, releasing enormous energy and producing harmless helium. For decades, fusion seemed out of reach, always 30 years away. The technical hurdles immense, temperatures hotter than the sun's core, plasma containment, like holding lightning in a bottle, made it a monumental challenge. Massive government projects moved slowly, and fusion remained a distant dream. But now, something fundamental has shifted. Private enterprise and venture capital have entered the race, pouring billions into agile startups. The dream is becoming an industry, a trillion-dollar race to power humanity's future. The conversation has moved from labs to boardrooms. The age of fusion is dawning and the world is watching. What was once a scientific fantasy is now a real possibility. The quest to harness the power of the stars is entering a new era. How do you build a star on Earth? Fusion demands temperatures over 100 million degrees, hotter than the sun's core. At these extremes, matter becomes plasma, a seething electrically charged gas. No material can touch it, so scientists use powerful magnetic fields to contain it. The tokamak, a donut-shaped chamber, uses electromagnets to create an invisible cage, suspending plasma away from the walls. Projects like ITER in France are building massive tokamaks to prove fusion can work at scale. But these machines are slow and expensive, taking decades to build. Now, innovators are asking, can we do it smaller, faster, and smarter? New materials and smarter magnets are opening the door for private companies to join the race. Private companies are transforming fusion, driven by the goal of net energy gain, where a reactor produces more energy than it uses. High-temperature superconducting (HTS) magnets are a breakthrough, allowing stronger fields in smaller devices. This means fusion reactors can shrink from stadium-sized to warehouse-sized, slashing costs and timelines. Commonwealth Fusion Systems, spun out of MIT, is building compact reactors aiming for the grid within a decade. Other companies like Helion are taking different approaches, using pulsed plasma collisions to generate electricity directly. Helion's progress has led to a power purchase agreement with Microsoft, signaling real commercial interest. The fusion race is now a hotbed of innovation, with diverse designs and rapid progress. The business world sees fusion as an investable near-term technology. The era of endless research is giving way to real-world deployment. Fusion's future is being built now, not in some distant tomorrow. Containing 100 million degree plasma is one of science's toughest control problems. Even tiny instabilities can crash the reaction in milliseconds. Enter artificial intelligence (AI) and machine learning now analyze data from thousands of sensors in real time. These systems predict and prevent instabilities, adjusting magnets and fuel faster than any human could. Google's DeepMind has already demonstrated AI control in real-world tokamaks. This digital partnership accelerates progress, allowing rapid virtual testing and optimization. Fusion reactors are now marvels of both physics and information technology. Human ingenuity and artificial minds are working together to tame a star. Achieving net energy gain will be historic, but it's just the beginning. Fusion reactors must withstand constant neutron bombardment, pushing materials science to its limits. The fuel cycle is another challenge. Deuterium is abundant, but tritium must be bred inside the reactor using lithium. Perfecting this closed fuel loop is essential for sustainability. Fusion must also compete economically with solar, wind, and advanced fission. Compact, efficient designs are key to making fusion affordable and scalable. For the first time, the path from experiment to power plant is clear. The question is no longer if, but when. Fusion will power our world. The age of the star is within reach, built in labs and factories today. We stand on the brink of a new energy revolution,